Stop wasting 30% of your petrol. The secret $1 fix manufacturers hid since 1979. The invisible thief, your car's biggest lie. Your car is lying to you right now. Every time you turn the key and drive away, a small component under your hood is quietly stealing money from your wallet. This isn't a conspiracy theory or a mechanic's scare tactic. This is about a tiny sensor that controls one of the most expensive aspects of car ownership: fuel consumption. The oxygen sensor is a small device that sits in your exhaust system. Its job is critical, yet invisible to most drivers. This sensor constantly monitors the amount of oxygen in your exhaust gases and sends signals to your engine's computer. Based on these signals, the computer adjusts how much fuel gets mixed with air before combustion. When this system works perfectly, your engine burns fuel efficiently. When it doesn't, you waste money with every mile. Here's where the problem begins. After approximately 30,000 miles of driving, something sinister starts happening. The oxygen sensor begins to drift. This drift is not a sudden failure. There are no warning lights on your dashboard, no strange noises from the engine, no smoke or rattling. The sensor simply starts sending slightly incorrect readings to your computer. These readings are still within acceptable ranges, so your check engine light never illuminates. Your car appears to run normally, but underneath this normalcy, your fuel consumption is quietly increasing. This drift phenomenon is the invisible thief. As the sensor ages, it becomes less responsive. It might tell your engine computer that there's more oxygen in the exhaust than there actually is. The computer responds by injecting more fuel into the cylinders, thinking the mixture is too lean. In reality, the mixture was fine. Now it's too rich. The excess fuel doesn't create more power. It just burns away, sending your money straight out the tailpipe. Studies have shown that a drifting oxygen sensor can increase fuel consumption by 20 to 30%. Imagine filling your tank and knowing that up to a third of that fuel will be wasted because of incorrect sensor readings. The financial impact accumulates silently. If you drive a vehicle that normally gets 30 miles per gallon, a drifting sensor could reduce that to 23 miles per gallon. Over a year of typical driving, this translates to hundreds of extra dollars spent at the pump. You notice your fuel gauge dropping faster than usual, but you blame traffic, weather, or driving habits. Meanwhile, the real culprit continues its theft undetected. Most drivers discover this problem only when the sensor fails completely and triggers the check engine light. By that point, they've already wasted months or even years of excess fuel. Mechanics charge significant labor fees to access the sensor, which is often buried deep in the exhaust system. The replacement sensor itself can cost anywhere from $50 to $200 depending on your vehicle. Add labor costs, and you're looking at a repair bill that makes you wish you had addressed the issue earlier. But here's the revelation that the automotive industry doesn't advertise. In many cases, you don't need to replace the sensor at all. The drift happens because of subtle changes in the sensor's electrical resistance. A simple $1 resistor, properly installed in the sensor signal wire, can compensate for this drift. This modification takes approximately 15 minutes for someone with basic automotive knowledge. It doesn't require special tools or a mechanic's expertise, just a resistor, a wire stripper, and the willingness to open your hood. This solution restores your sensor's accuracy without replacing the entire unit. Your engine computer receives the correct signals again. Fuel mixture returns to optimal levels. Your fuel economy improves back to factory specifications. That 20 to 30% waste disappears. Every tank of fuel goes further. Every trip to the pump costs less. The invisible thief has been caught and stopped. Your car's oxygen sensor is lying to you right now, and that lie is costing you money every single day you drive. The question isn't whether this is happening. The question is how long you'll let it continue before taking 15 minutes to fix it. The 1979 files Ford's hidden truth. The story begins in Dearborn, Michigan in the year 1976. The automotive capital of America was facing a crisis that would reshape the entire industry. Congress had just passed the Clean Air Act, and its regulations were about to hit car manufacturers like a sledgehammer. The law mandated dramatic reductions in vehicle emissions. Carbon monoxide, hydrocarbons, and nitrogen oxides all had to be slashed to levels that seemed impossible with existing technology. The solution came in the form of a device that most Americans had never heard of: the catalytic converter. The catalytic converter was a sophisticated piece of emissions control equipment that used precious metals like platinum and palladium to chemically transform harmful exhaust gases into less toxic substances. But this device had a critical requirement. It could only function properly when the engine's air-fuel mixture maintained an extremely precise balance. This balance is known in engineering circles as the stoichiometric ratio. The stoichiometric ratio for gasoline combustion is 14.7 parts of air to 1 part of fuel. This exact proportion ensures complete combustion, where all the fuel molecules combine with all the available oxygen molecules, producing maximum energy with minimum waste. When an engine runs at this precise ratio, the catalytic converter can do its job effectively. The exhaust gases entering the converter have the ideal chemical composition for the catalyst to work its magic. Stray too far from this ratio in either direction, and problems emerge. If the mixture becomes too lean, meaning too much air and not enough fuel, the engine loses power and can suffer damage from excessive heat. If the mixture becomes too rich, meaning too much fuel and not enough air, unburned fuel passes through the engine and overwhelms the catalytic converter. Fuel economy plummets, emissions skyrocket, and that precious fuel you paid for simply burns away without producing useful work. Maintaining the 14.7-to-1 ratio became absolutely critical for meeting emissions standards while preserving fuel efficiency. This is where the oxygen sensor entered the picture. Engineers developed this sensor specifically to monitor exhaust gases and provide real-time feedback to the engine computer. The computer would adjust fuel injection on the fly, constantly chasing that perfect stoichiometric ratio. It was an elegant solution, and it worked beautifully when the sensors were new. But then the problems started appearing. In 1979, an engineer named David Mercer was working in Ford's powertrain research division. Mercer had been conducting long-term durability tests on the new oxygen sensor-equipped vehicles. What he discovered should have been front-page news for every car owner in America. Mercer documented that oxygen sensors began to drift from their calibrated readings after approximately 30,000 miles of use. The drift was gradual and predictable. The sensors didn't fail catastrophically. They simply became less accurate over time, reporting incorrect oxygen levels to the engine computer. Mercer's findings were thorough and alarming. He calculated that this sensor drift could increase fuel consumption by 20 to 30% over the remaining life of the vehicle. He projected the cumulative cost to consumers in the billions of dollars annually across the entire fleet of American vehicles. His research included recommendations for periodic sensor replacement and potential circuit modifications to compensate for the drift. The documentation was comprehensive, technically sound, and deeply concerning. But here's where the story takes a dark turn. Mercer's research was filed away in Ford's internal technical libraries. The information was classified as proprietary engineering data. It circulated among engineers and technical staff who worked on emission systems and fuel management, but it never made its way into owner's manuals. It never appeared in maintenance schedules. Dealerships weren't trained to look for it. Consumer advocacy groups never heard about it. The general public remained completely unaware that their vehicles had a ticking time bomb of wasted fuel built into their exhaust systems. This wasn't just a Ford problem. General Motors had similar research. So did Chrysler, Toyota, Honda, and every other manufacturer producing vehicles with oxygen sensors. The sensor drift phenomenon was well documented across the industry. Engineers at competing companies were reading the same test results and reaching the same conclusions. This was an open secret in the automotive engineering community. Technical papers mentioned it in academic journals that ordinary consumers never read. Industry conferences discussed it behind closed doors. But the information never bridged the gap between engineering departments and the car-buying public. The suppression wasn't necessarily malicious. It was simply business as usual in an industry where technical knowledge remained compartmentalized. Manufacturers had no legal obligation to inform consumers about gradual efficiency losses that didn't trigger safety concerns or emissions failures. The sensors still worked well enough to pass emissions tests. The cars still ran. There were no recalls, no lawsuits, no regulatory pressure to disclose this information. So the silence continued for decades, and millions of drivers paid the price at the pump without ever knowing why. The $100 billion silence, the $1 trillion deception. At an average fuel price of $3.50 per gallon, this waste translates to $437 annually for a modest estimate. In regions with higher fuel prices, or for drivers who cover more miles, the annual loss climbs to $668 or more. This isn't a one-time expense. This is money hemorrhaging out of your fuel tank year after year for as long as you own that vehicle. Over a typical vehicle ownership period of 10 years, a single driver loses between $4,000 and $6,000 to sensor drift alone. Now multiply that by the number of vehicles on American roads. Over 270 million registered vehicles, most of them equipped with oxygen sensors that are slowly drifting away from calibration. The mathematics becomes staggering. Even conservative estimates place the annual excess fuel consumption in the billions of gallons. The financial cost to consumers reaches into the tens of billions of dollars every single year. And this has been happening for 45 years, since oxygen sensors became standard equipment. When you calculate the cumulative cost since 1979, the number is almost incomprehensible. American drivers have spent approximately $4.5 trillion on excess fuel consumption caused by oxygen sensor drift. $4.5 trillion. That's more than the entire gross domestic product of most countries. That's enough money to rebuild the entire American infrastructure system. That's a sum so vast, it's difficult for the human mind to grasp. And it all disappeared into fuel tanks, 1 gallon at a time, because of a problem that was documented and understood but never disclosed to the public. The silence wasn't accidental. It was economically motivated by three powerful industries that profited immensely from keeping consumers in the dark. First, the oil industry benefited directly from increased fuel consumption. Every percentage point of reduced efficiency translated to billions of additional gallons sold annually. The oil companies weren't manufacturing defective sensors, but they certainly had no incentive to publicize a problem that boosted their sales. More fuel consumption meant more revenue, and sensor drift was delivering exactly that. Second, car manufacturers had their own reasons for silence. Vehicles with drifting sensors still passed emissions tests in most cases. They still met warranty requirements. They still satisfied regulatory standards for the first 50,000 miles when most emissions testing occurred. Addressing sensor drift would have required more frequent replacements, more sophisticated sensor designs, or compensation circuits that added cost to every vehicle. Why invest in solving a problem that consumers didn't know existed and that regulators weren't enforcing? The business case for disclosure simply didn't exist. Third, and perhaps most cynically, the dealership and automotive service industry had discovered a gold mine. When sensors eventually drifted far enough to trigger a check engine light, customers came in for repairs. Dealerships could charge $300 or more for sensor replacement, including parts and labor. The sensor itself might cost $50 to $100 wholesale, but the labor charges and diagnostic fees added up quickly. This created a steady stream of service revenue that dealerships counted on. A simple $1 resistor fix would eliminate this entire revenue stream overnight. No service advisor in their right mind would suggest a $1 modification when they could sell a $300 repair. The professionals already knew about this issue and were quietly fixing it. Professional engine tuners who worked on race cars and performance vehicles understood oxygen sensor drift intimately. They compensated for it routinely using resistor modifications, signal conditioners, and custom tuning. Fleet managers overseeing hundreds of vehicles for corporations, delivery companies, and government agencies had done the math. They knew that addressing sensor drift could save millions of dollars annually in fuel costs. Many implemented their own monitoring and compensation systems to maintain fleet efficiency. Racing teams were particularly sophisticated about this. In motorsports where fractions of a percent in efficiency could mean the difference between winning and losing, oxygen sensor accuracy was non-negotiable. Teams used high-end wideband oxygen sensors and regularly calibrated them or installed compensation circuits. The knowledge existed. The solutions existed. The professionals were using them every day. But this information remained locked within technical communities that had no incentive to share it with ordinary consumers. The silence persisted because it was profitable for everyone except the people paying for fuel. Oil companies sold more gasoline. Manufacturers avoided warranty costs and design complications. Dealerships generated service revenue, and consumers remained blissfully unaware that their vehicles were designed to become progressively less efficient over time. The system worked perfectly for everyone making money from it. The only losers were the drivers who trusted that their vehicles were operating as efficiently as possible and who never imagined that a documented engineering problem was quietly draining their wallets every time they drove. The physics of the fix, how a $1 resistor works. To understand the solution, we must first understand the problem at the electrical level. An oxygen sensor is essentially a voltage generator. When it detects oxygen-rich exhaust gases, indicating a lean fuel mixture, it produces a low voltage signal around 0.1 volts. When it detects oxygen-poor exhaust gases, indicating a rich fuel mixture, it produces a high voltage signal around 0.9 volts. The engine control unit reads this voltage and makes instantaneous decisions about fuel delivery based on what it sees. The ideal operating point, the sweet spot where combustion is most efficient and the catalytic converter works optimally, sits right in the middle at approximately 0.45 volts. At this voltage, the sensor is telling the computer that the air-fuel mixture is at the stoichiometric ratio of 14.7 to 1. The computer maintains this balance by constantly adjusting fuel injector pulse width, adding fuel when voltage drops below 0.45 volts, and reducing fuel when voltage rises above it. This feedback loop happens dozens of times per second, creating a dynamic equilibrium that keeps your engine running at peak efficiency. But here's where sensor aging destroys this delicate balance. As an oxygen sensor accumulates miles, its ceramic element becomes contaminated with deposits from fuel additives, oil vapor, and combustion byproducts. These contaminants don't destroy the sensor's ability to detect oxygen. They simply alter its electrical characteristics. The sensor becomes biased toward producing lower voltage readings across its entire operating range. What should read 0.45 volts at stoichiometric might now read 0.35 volts. The sensor hasn't failed in any detectable way. It still produces voltage. It still responds to changes in exhaust oxygen, but its baseline has shifted downward. This creates what engineers call the lean illusion. The engine control unit receives a signal of 0.35 volts and interprets this as meaning the mixture is too lean, with too much air and not enough fuel. The computer has no way of knowing that the sensor itself is lying due to contamination. It trusts the sensor implicitly because that's how it was programmed. So the computer does exactly what it's designed to do. It compensates for the perceived lean condition by commanding the fuel injectors to stay open longer, injecting more fuel into the cylinders with each cycle. But remember, the actual air-fuel mixture was already correct. The sensor was simply reporting it incorrectly due to voltage bias from contamination. By adding extra fuel, the computer has now created a genuinely rich mixture. The engine is burning more fuel than necessary for the amount of air entering the cylinders. This excess fuel doesn't produce additional power because there isn't enough oxygen to burn it completely. Instead, it passes through the combustion chamber partially burned and gets expelled into the exhaust system. Your fuel economy drops by 20 to 30%, and you have no idea why, because everything feels normal. The conventional solution is to replace the sensor with a new one that hasn't yet developed this voltage bias. But replacement costs hundreds of dollars and only solves the problem temporarily. Within another 30,000 miles, the new sensor will begin drifting just like the old one. You'll be back at the dealership for another expensive replacement. This cycle continues for the entire life of the vehicle, costing you thousands of dollars in unnecessary parts and labor. The unconventional solution exploits a basic principle of electrical engineering called the voltage divider effect. By installing a resistor in series with the oxygen sensor's signal wire, you create a circuit that mathematically shifts the voltage signal upward by a fixed amount. If your contaminated sensor is producing 0.35 volts when it should be producing 0.45 volts, a properly sized resistor can add exactly 0.1 volts to that signal before it reaches the engine control unit. The computer now sees 0.45 volts, which is exactly what it should be seeing. The lean illusion has been corrected, and the computer stops overcompensating with excess fuel. The resistor values that accomplish this correction typically range from 33 ohms to 68 ohms, depending on your specific vehicle and sensor design. These are standard components available at any electronic supplier for less than $1. A 33 ohm resistor provides a smaller voltage shift, suitable for sensors with mild drift. A 68 ohm resistor provides a larger voltage shift for sensors with more severe contamination. Some vehicles respond best to intermediate values like 47 ohms or 56 ohms. The exact value depends on how much voltage correction your particular sensor needs. Installing this resistor is remarkably simple. You locate the oxygen sensor's signal wire, which is typically a single wire coming from the sensor that carries the voltage signal to the computer. You cut this wire, strip a small section of insulation from both ends, and solder the resistor in line so that current must flow through it on its way to the computer. The resistor adds a small voltage drop that offsets the sensor's downward bias. You insulate the connection with heat shrink tubing to protect it from moisture and heat, and the job is complete. 15 minutes of work, $1 in parts, and your fuel economy returns to factory specifications. The beauty of this fix is that it doesn't replace or modify the sensor itself. The sensor continues doing exactly what it was doing before, producing the same biased voltage it always produced. But now that voltage passes through a compensation circuit that mathematically corrects the bias before the signal reaches the engine control unit. The computer receives accurate information, makes correct fueling decisions, and your engine returns to optimal efficiency. The invisible thief has been caught, not by replacing the sensor, but by outsmarting its deception with basic electrical engineering that costs less than your morning coffee. Reclaiming power. The step-by-step driveway hack. You don't need a mechanic's license or a fully equipped garage to fix this problem. You need less than $50 in tools and the willingness to spend 15 minutes under your hood. The toolkit is simple and affordable. A basic digital multimeter costs around $15 at any hardware store. A pack of resistors in various values costs less than $5 from an electronics supplier or online retailer. You'll need a wire stripper, electrical tape, or heat shrink tubing, and a soldering iron if you want a permanent installation. If you don't want to solder, crimp connectors work almost as well. Every item on this list is available at your local auto parts store or hardware store. The first step is locating your upstream oxygen sensor. Most vehicles have multiple oxygen sensors, but you only care about the one located before the catalytic converter in the exhaust stream. This is called the upstream sensor, or sensor 1. It's the sensor that directly controls fuel mixture. The downstream sensors after the catalytic converter only monitor converter efficiency and don't affect fuel delivery. Your upstream sensor is typically located on the exhaust manifold or in the exhaust pipe within the first foot of the engine. It looks like a spark plug with a wire connector attached. On most vehicles, you can see it from above by opening the hood. On some, you might need to get underneath the car or remove a plastic engine cover. Once you've located the sensor, start your engine and let it warm up to normal operating temperature. This is critical because oxygen sensors only produce accurate voltage when they're hot. Cold sensors give meaningless readings. After 10 minutes of idling or a short drive around the block, your sensor should be at operating temperature. Now comes the diagnostic step that tells you whether you need this fix. Set your multimeter to measure DC voltage in the 0 to 1 volt range. Locate the signal wire on your oxygen sensor. This is usually a single wire, often black or gray, separate from the heater wires that power the sensor's heating element. Carefully backprobe the signal wire connector without disconnecting it. You need to measure voltage while the sensor is actively communicating with the computer. Watch your multimeter reading as the engine idles. A healthy oxygen sensor should fluctuate rapidly between 0.1 and 0.9 volts, crossing through 0.45 volts regularly as the computer adjusts the fuel mixture. If your sensor is reading consistently below 0.3 volts or consistently above 0.6 volts, without much fluctuation, it has drifted from calibration and is causing the computer to overcompensate with excess fuel. If testing confirms your sensor has drifted, it's time to install the correction resistor. Turn off the engine and disconnect the battery to prevent any electrical issues while you work. Locate the signal wire between the oxygen sensor and the computer. You'll be cutting this wire and installing the resistor inline. Choose your starting resistor value. For most applications, a 47 ohm resistor works well. If you want to be more precise, you can calculate the exact value based on your measured voltage, but 47 ohms is a safe middle ground that corrects most drift without overcorrecting. Cut the signal wire at a convenient location where you have room to work. Strip about ½ inch of insulation from both cut ends. If you're soldering, twist one leg of the resistor to one wire end and solder the connection. Do the same with the other resistor leg and the other wire end. Cover each soldered joint with heat shrink tubing and use a heat gun or lighter to shrink it in place. This creates a waterproof, heat-resistant connection that will last for years. If you're not comfortable soldering, use crimp connectors designed for automotive wiring. They're not quite as reliable long-term, but they work perfectly well for this application. With the resistor installed and insulated, reconnect your battery and start the engine. Let it warm up again and repeat your voltage measurement. You should now see readings closer to 0.45 volts with normal fluctuation above and below that midpoint. The computer is receiving corrected information and should be adjusting fuel delivery accordingly. If the voltage is still too low, you can try a larger resistor value like 68 ohms. If it's now too high, step down to 33 ohms. Fine-tuning takes experimentation, but most vehicles respond well to values in the 47 to 56 ohm range. The real test comes when you drive. Reset your trip odometer and fill your tank completely. Drive normally for the next few hundred miles, mixing highway and city driving just as you usually would. When the tank is nearly empty, fill it again and calculate your actual fuel economy by dividing miles driven by gallons consumed. If your sensor drift was significant, you should see improvement of 15 to 25% compared to what you were getting before the fix. A vehicle that was averaging 22 miles per gallon might now achieve 28 or even 30 miles per gallon. That's real money staying in your pocket with every mile you drive. One important compatibility note: this fix works best on vehicles manufactured before 2005 that use simple analog oxygen sensors. These older sensors produce a straightforward voltage signal that responds predictably to resistor compensation. Newer vehicles from 2006 onward often use more sophisticated wideband oxygen sensors with digital communication protocols. These sensors are more resistant to drift, but also more complex to modify. If you have a newer vehicle, this resistor hack might not work as intended. You'll need to research whether your specific make and model uses traditional narrowband sensors or newer wideband technology. This isn't just about saving money on fuel. This is about reclaiming power from an industry that has hidden the truth from consumers for 45 years. Every time you install one of these resistors and restore your vehicle's efficiency, you're taking back what the automotive and oil industries have been quietly stealing. You're refusing to accept planned obsolescence as inevitable. You're demonstrating that consumers don't have to be victims of information asymmetry when the people who know the truth choose silence over disclosure. Share this information with every driver you know. Post it on social media. Talk about it at family gatherings. Mention it to coworkers. The only way to end this expensive silence is to make the knowledge so widespread that the industries profiting from it can no longer pretend the problem doesn't exist. When millions of drivers understand that a $1 resistor can save them hundreds of dollars per year, the economic incentive structure changes. Dealerships will have to adapt. Manufacturers will have to address the issue openly. And consumers will finally have the power to make informed decisions about their vehicle maintenance. This simple modification represents something larger than fuel economy. It represents the democratization of technical knowledge that was deliberately kept from the people who needed it most. It proves that complex problems sometimes have simple solutions, and that those solutions become possible when information flows freely instead of being locked away in corporate technical libraries. Take 15 minutes, spend $1, and reclaim the efficiency that should have been yours all along.